Okay, so here's an example of one of the questions you might see. It says, using the table of standard reduction potentials, predict whether 1 molar nitric acid will dissolve gold metal to form a 1 molar gold 3+ ion solution. Okay, so before we even go about solving this problem, one thing you need to be careful of is the phrasing. The phrasing of the question is really important when it comes to electrochem, because it may ask you for just the overall cell potential, or it may ask you for the cell potential and to balance the equation. I know the quests have both types of questions. And here it doesn't say either, it just says predict. So what predict really means is that we need to find our cell potential. So if you see predict, that means find the cell potential. If we know the cell potential, we can figure out if this is spontaneous or not spontaneous. So I took the liberty of already looking up one of the half reactions. It's not one that you would find on your table. So we have 4H plus 3 electrons plus the nitrate ion gives us NO plus 2 waters, and that has a positive potential of 0.96 volts. The other one we need to figure out the process of gold becoming gold 3+. Let's go back to our reduction potential. It's actually this third one here. It says Au3 plus 3 electrons gives us gold, and it has a cell potential of 150. So we write that here. We've got Au3 plus and 3 electrons, and we become gold. All right, Au solid, and this is potential of 1.50. Okay, so we want to know if this will dissolve gold metal. So first things first, we need to look at what we have as our reactants. In our first half reaction, the nitrate ion is on the correct side. We want that as a reactant. But if we look at our second one here, you see that the gold ion is on the reactant side. But we don't want gold as a reactant, we want it as a product. We're trying to figure out, will this react in such a way with gold metal such that we get gold ions dissolved in a solution? Well, since these are on the wrong side, what we can do is we can reverse it. So the way we would reverse is very similar to some of the things we did with the Hess's law. So you just reverse. AuS gives us Au3+. I meant to write the aqueous symbol in there before. It is aqueous plus 3 electrons. And if we reverse it, the only thing we have to do to our cell potential is make it negative. Okay? Now, normally I would say it's good practice to go out and balance this whole thing, but in the end of the day, that's not really what we want to know. It would just be wasting yourself some time. What we want to know is whether or not this will be spontaneous. So, to check to see if it's spontaneous, we just need to add our half reactions together, whether they're balanced or not. The balance does not affect the cell potential. So we look, we add everything together. I'm not even going to write out the reaction down below. What I really care about is this section here. If I add these together, 0.96 plus a negative 1.5, we end up getting a cell potential of E equals to negative 0.54 volts. So then we need to be able to explain it. What does a negative cell potential mean? Is that going to be spontaneous or non-spontaneous? Right, it is not spontaneous. So no, this would not form gold ions. A negative cell potential results in a non-spontaneous reaction. Okay. So, the next few examples come straight from Renee McCormick and the Namesy site. I will add in a couple of my own as well. These are good problems to look at. First one, it says, consider a galvanic cell on the reaction aluminum 3 plus magnesium, and it gives us aluminum solid and magnesium 2 plus. We want the balanced cell reaction and calculating the cell potential for the cell, E naught. Okay, so let's look up our half reactions. All right, and we want to look up our half reactions as is. So you have to scroll through our table. This is the hardest part, trying to find them all. Okay, so we have magnesium 2 plus with, it's down the bottom part, half of this table. So magnesium 2 plus plus 2 electrons gives us magnesium solid, and that's negative 2.37. So we can copy that down. We've got one half reaction, Mg2 plus 2 electrons, and we get magnesium solid, and a cell potential of negative 2.37 volts. And the other one we had, which is on your chart, please refer back to it, Al3 plus 3 electrons, and you get Al solid. And that cell potential was 1.66, I believe, and negative 1.66, sorry. Negative 1.66 volts. And that came from our chart. It's actually right above, above the magnesium 2 plus. Okay. So, first things first. We need to identify which one is being reduced and which one is being oxidized. So that's easy. Remember that oxidation is the loss of electrons. If we look at magnesium, magnesium is losing electrons. So here it is uncharged, and over here it becomes positive. So if it becomes positive, that means it is losing electrons. Magnesium is our oxidation reaction. That's a terrible O, I apologize. Our oxidation reaction. And if we look at aluminum, aluminum goes from 3 plus to neutral, which means it is gaining electrons. This is our reduction reaction. Okay? So we need to make sure that these reactions are going in the right order. We said reverse the oxidation half reaction. We know we want to do that, 1, because we said so in our rules, 2, because we see that the magnesium is solid is in the product side here, and we need it on the reactant side. So let's go ahead and reverse. We've got Mg solid, and we get Mg2 plus and 2E minus. Anytime we reverse, we're going to need to change our sign. Okay, and we change our sign, so let's cross this one out. We're done with it. Okay. Now, the other thing we need to do is balance. So we don't have any oxygens or anything to balance. We don't have any waters or H pluses we need to add in. So we can skip straight to the step where we balance our electrons. So you need to find the common denominator. We know that if we multiply this by 3, this whole reaction, and we multiply our aluminum reaction by 2, we should be able to get electrons that will cancel out. So we have our balance, Al3 plus 6E minus gives us 2 aluminum solid. Remember that your cell potential does not get affected by multiplying, so it stays the same. We also have 3 magnesium solid. and 6 electrons. Cell potential doesn't change. Okay, 2.37 volts. Make sure we got that point there. Okay, well now we know that the electrons will balance, so we can go ahead and add everything together. So when we add, our 6 electrons will cancel out, and we'll be left with our balanced equation, and we want to add our cell potentials together. So when you add them together, we should be able to figure out whether or not this is in fact going to be spontaneous. So we've got 2 Al3 plus, that's aqueous, plus 3 magnesium solid, and that gives us 2 aluminum solid, plus 3 magnesium 2 plus, and when we add these cell potentials together, we end up getting a positive 0.71 volts. What does that mean? Will this reaction happen on its own? Yes, this reaction will happen on its own because it has a positive cell potential. We have balanced it, and we have given the cell potential. On the quest, you may be asked a specific coefficient, so you'll still have to balance the entire thing, and then you'll give the cell potential for the cell. Okay, here's another example. This one, I don't believe they gave the cell potential to you in your chart, or the reduction potential to you in your chart, so you may have to look up some of these. We try to give you as many as possible. I will look these up though. So it says a galvanic cell is based on this reaction with the permanganate ion, that's MnO4 minus. We've got H plus, and we've got chlorate and perchlorate ions, and then manganese 2 plus and H2O. So balanced cell and reaction. All right. The first one's easy. We want the MnO4 and Mn2 plus. So let's look. So it's not on this one. But it might be back on the one that was in here earlier. Aha. So down at the down in the middle here, it says MnO2 plus 4H plus 2E. This one right here. It gives us Mn2 plus and 2 waters with a cell potential of 1.21. Okay. So let's write our 2 half reactions. We've got, let me change this back to black. All right, so MnO4 minus aqueous plus H plus. Oh. Sorry, that was 8H plus. Plus 8H plus 5 electrons, and we get manganese 2 plus and 4 waters. Okay, and our cell potential is 1.51 volts. Okay. All right, the other half reaction we need is this one with the chlorate becoming a perchlorate ion. This is the one that I had to look up. So I looked it up. It was on this site here. Where is it? And they actually had it in reverse order. They had chlorate becoming, or perchlorate becoming chlorate. So that is okay for the purpose of what we're doing. So I'll transfer that over. I had the chlorate ion aqueous plus 2H plus 2 electrons, and we get ClO3 minus aqueous plus 1 water. 1 water. And my cell potential here is 1.19 volts. 1.19 volts. Okay. So we need to identify the difference between the reduction and the oxidation. This one's fairly easy. You can just get used to figuring out manganese fairly easy. Anytime you have MnO4, we know we've got 4 times -2, which gives us 8, -8. So some number plus -8 is going to give us our charge of -1. So manganese has to be +7. We had +7 and a -8, we get our -1. So if we look at manganese from up here, it goes from +7 down to +2. It's really easy to see that manganese is being reduced here. Okay, so we can label that as our reduction step. All right, and if this is our reduction, then this can be our oxidation. You can even just look at it from the stance of, we see the manganate ion here. We see that manganate ion on the reactant side, whereas my perchlorate ion should be on the product side. So we know we're going to have to switch the second equation because the ions are on the wrong side. So let's reverse this. All right, so I'll do that in a different color. Do blue, like the blue. So ClO3 minus plus my water. All right, and I'll get ClO4 minus plus 2H plus and 2 electrons. And when I do that, remember my cell potential becomes negative. Okay, so I got a -0.19, and this is gone. All right, now I need to balance my electrons. What do 2 and 5 have in common? We've got to multiply by 10. Or not multiply by 10, but multiply such that we get 10. So I want to multiply this whole reaction by 5. I want to multiply this reaction by 2. Okay. Actually, I put the brackets in the wrong spot down here. I apologize. All right, because we don't multiply our E values at all. Okay. So let's pull all the parts down. We've got 2. Oh, that's hard to read. Let's pick a different color. Let's do purple. All right. There you go. 2 MnO4 aqueous plus 16H plus 10 electrons. And we've got 2 manganese 2 plus and 8 waters. Okay. E value stays the same. Remember, that does not multiply. And then we've got a remainder. I have H2O. Okay. And this is still a -1.19 volts. All right. We have the proper amount of electrons. We can add everything together now. This one we have to be careful with, though, because we have waters on both sides and we have H pluses on both sides. That will definitely cancel out. So let's cancel out everything first. We've got 10 on the left, 10 on the right. With H plus, we've got 10 on the right. We can cancel out 10 of these and make that a 6. And then we've got 5 waters on the left. We can cancel this out and make this a 3. So in the end, we get 2 MnO4 minus plus 6 H plus 5 ClO3 minus And then we get 5ClO4 minus plus 2 manganese 2 plus and 3 waters. Okay, that's our balanced reaction, and then we can add our cell potentials together. When we add our cell potentials together, we get an E value of 0.32 volts. This is also a spontaneous reaction. This is one of the last ones, I believe, that's in the Namesy video. This one is a really good problem because not only do we have to figure out our cell voltage, but we have to draw it too. So let's read this carefully. This one has a wealth of information, and we have to pull in some knowledge that we learned earlier on. It says calculate the cell voltage for the galvanic cell that would utilize silver metal and iron 2 ion and iron 3 ion. Draw a diagram of the galvanic cell for the reaction and label it completely. So, we have some information here that makes this a little bit challenging. We're going from iron 2 plus to iron 3 plus ion. Remember that we said when we go ion to ion, we are going to require an inert electrode. So platinum would be fair game here. So that'll be important for when we draw. So platinum electrode, you can use that as the default. Platinum is usually pretty solid. Platinum electrode, because ion to ion. The other time you could use it is if we were dealing with a gas. We're not really dealing with a gas here, so that's okay, but we're going from ion to ion. So we need a couple of half reactions here. They mention silver metal, but they don't talk about the silver ion. We will get there, we'll incorporate that. But let's go back to our table here. So we have the cell potential for silver. We got Ag plus with 1 electron gives us Ag metal, silver metal, and that's a 0.8 reduction potential. So we've got Ag plus an electron, and we get ding, this is solid, and our reduction potential is 0.80 volts. And then the other one, if we look, we got to find the iron that goes from Fe3 plus to 2 plus, which is actually right below it. That has a volume of 0.77. Iron 3 plus an electron gives us iron 2 plus, and our cell potential is 0.77 volts. Okay. So we have to make a couple assumptions here. One, we want this to be spontaneous, so we're going to need to make these potentials add up together to be a positive number in some shape or form. So that will help dictate which we are going to reverse. So we're using silver metal. If we were to reverse silver metal, we would have a negative 0.8. If we add negative 0.8 to a positive 0.77, we would get a negative number, so that would not work. We would have to reverse this one here, the one with the ions. If we reverse that one, we would be able to get a positive cell potential that would work for us. Alright, if we were to add these together, electrons balance out. There's actually very little other balancing we have to do. We have Ag plus, Fe2 plus, and then we would get Fe3 plus ion plus solid silver. We add these together, we get our cell potential is 0.03 volts. That's the easy part. The tricky part is now drawing it all. What? How do we draw this? Oh my goodness. Don't worry, we'll be okay. We have to remember the parts of our galvanic cell as we talked about earlier, and we need to include all of them. So, let's start with our beakers here. All right. So, some keys here. They say they want to involve silver metal. That means that the silver metal will be one of your electrodes. So I'm going to draw, this is going to be my silver metal. I know silver metal is not blue. I'm going to write Ag, Ag. And the other thing we said is that since we have this ion to ion thing going on, we're going to have a platinum electrode as well. So platinum electrode, PT. And we need to have a wire connecting them. So the wire, okay. So as it stands, the flow of electrons can only go from anode to cathode, but there's no way for them to make it back, and the balance of the solution would not remain neutral. So we need to add our salt bridge, okay? So the salt bridge. Look something like this. Okay, this is our salt bridge. If you want to label it salt bridge, you can. Salt bridge. Okay. And one other thing I forgot actually is when you draw your wire, you're going to need a little voltmeter. Voltmeter there. We said our volts is 0.03 volts. Okay. So we need to figure out which is the cathode and which is the anode. So remember, reduction occurs at the cathode. So we need to go back to our reaction and see what's happening here. If we look, Ag plus is being reduced to silver metal. So since reduction occurs at the cathode, this is my cathode here. Cathode. You have to make sure you label that. And if that's the cathode, then the other is my anode. All right. So which way do the electrons flow? Electrons should flow anode to cathode, right? Okay. And now the trick, we also need to make sure we label concentrations. We can assume this is at standard conditions. So we can say 1 molar for our solutions. And with cathode, I'm just going to write positive. With the anode, I'm just going to write negative charge, okay? So the negative charge is leaving, going up, across, and then down onto the silver, okay. In our salt bridge, potassium nitrate's a very popular thing, popular salt that you would see. K plus. I'll have another nitrate in here. There you go. So all of the positives would migrate towards one end, all of the negatives would migrate towards the other end. So we have the reduction of our silver ions going on here. So in solution, we know we have to have a bunch of silver ions. Okay. And on the other side of things, if we got to go back to our equation, we see that the iron 2 plus is being oxidized. So iron 2 plus is my reactant that needs to be in solution. we go based off of our reactants, right? So we saw our reactants were iron 2 plus and Ag plus. Okay. So this is what a correctly labeled picture looks like. Now, what's actually happening here once we get started is really, really cool. As electrons are flowing from the platinum anode to the silver cathode, it means that negative charge is flowing into this solution here, where we have all of these silver ions. These things are getting neutralized. As we throw more electrons in, these charges are going away, and we're being left with silver metal. That silver metal will plate out onto the cathode, and this will start to get larger as more silver plates out onto it. As this is happening, though, this beaker of solution is going to start to become neutral. The way we prevent it from becoming neutral in that sense is that we have these potassium ions come down from our salt bridge to balance out our charge. So even though electrons are flowing and neutralizing the silver, there's still positive charge that will build up here from my salt bridge, my potassium. Same thing happens on the other end. As electrons are going up this way, these are turning into 3 pluses because they're being oxidized. We're losing electrons, right? 3 plus. So now we're building up charge on the other side, and we need to balance that charge out with our nitrate ions. So in effect, these two systems together create this loop. This is completing our circuit. And electrons can continue to flow in this manner and provide a voltage of 0.03 volts. It's really cool. Okay. So you may be asked to draw something like this, not on a quest necessarily, but you may be asked to draw this on the AP test. This is a fair test question. They really like using diagrams. That's the new thing. As you do your electrochemistry for your response packets, you'll see that they don't have you do that many diagrams early on, but as we get into the more recent years, diagrams are a big thing. Okay. So we've got a few more examples. These ones are fairly straightforward. We just need to figure out the electrical potential. Notice it says you do not have to balance. So let's find our half reactions. You can refer to your tables. I already have them written out, so I will just pull. I know that I've got Na plus, E minus, and my potential negative 2.71 volts. My other one is lead oxide. Two plus and 2 waters. And my cell potential is 1.46. So I know that this here is being reduced. If we look at the oxidation state, the oxidation is going down to a 2 plus. And I know that on this side, I am becoming oxidized because I'm losing electrons and becoming positive. I'll switch my oxidation. So my E becomes a 2.71 volts, and I want to add it to 1.46. I should get a total of about 4.17 volts. It's a lot of volts. And you're done. I don't even need to balance the rest of this. Go ahead and try the same one for iron 3 plus and magnesium reacting to form magnesium 2 plus and Fe2 plus. Okay. We've got Fe3 plus, and your 1 electron, and Fe2 plus, and our potential 0.77 volts, and then magnesium 2 plus, 2 electrons, and we get magnesium metal. Again, we don't even have to balance these, even though the electrons are different. We just have to switch some signs. So I know that this normally is a 2.37, and I want magnesium as a reactant, so I need to reverse this one. All I need to do is change my sign, and then add these together. I'm sorry, my sign originally was negative 2.37, so I changed my sign. And I get a positive 3.14 volts. Boom. Okay. So another set of problems you might have is trying to figure out if one thing is capable of reducing the other. If you look at the reduction potentials in the table, we should be able to figure out the cell potential if these things reacted. I would look up the cell potentials for each first. And remember that you're going to have to switch at least one, and that the result is going to have to be positive when you add them together. So go ahead and try these on your own. All right. The cell potential for hydrogen is 0.00 volts, and our cell potential for Ag plus being reduced to silver metal is 0.80. The one that you would have to reverse is this one here. When you reverse 0, it's still 0. No matter which way you spin it, when we add these together, we get a positive reduction potential. Yes, it is capable of reducing. Okay. Same thing with this one, but with nickel, this is where we get tricky. When we look at nickel reducing, it was a negative number, and this is already in the right order for nickel, so we can't reverse the sign of this, but we can reverse the sign of this, but it's still 0. When we get a negative 0.25, no, this is not going to reduce. So it does not work that way on our series. Okay. All right, this next one is a little challenging because we have the Fe2 plus. We want to know if it can reduce the VO2. Is that on this table here? I don't see it here. I think it was on the other one here. Aha, this one. VO2, this one here. So we want to reduce VO2 plus. So this is currently in the reverse order. We know we're going to have to reverse this one. So we know we're going to have a negative 1.00. All right, negative 1.00 volts. And then we want to find iron 2 plus. Iron 2 plus, standard reduction potential for iron 2 plus is down here. We've got Fe2 plus 2 electrons gives us iron metal, and that's a negative 0.44. This is already a negative 0.44. And since we flipped the sign of this one here, we have to add these as is. Negative 1.44, no. These are not capable of reducing each other. Okay, we want to do the same thing here. So we've got the negative 0.44 volts, right? And we want to figure out chromium 3+. Can chromium 3+ be reduced? Chromium 3+ can be reduced to 2+, or it can also be reduced, I believe it's up here, more at the bottom here. Where did it go? We can reduce chromium 3+ straight to chromium, and it has a 0.74 value, or we can reduce it from 3+ to 2+, in case it would be a 0.41 value, negative 0.41. So we're looking at negative 0.41 or negative 0.76. Doesn't specify. Negative 0.71 or negative 0. What was the other one? Sorry. 0.41 or 0.774. Sorry. 0.74 or 0.41. Okay. So these numbers again have to stay as is, but we can reduce this one. Even if we make this positive, when we add it with this one, we get a negative 0.30. If we add it with this one, we would get a 0.03 volts. So it depends. If you are just trying to reduce the charge from 3 to 2, from 3 to 2 it would work. But if you're trying to reduce the charge all the way down from 3 to neutral, so this is from 3+ to 2+, and we can say yes, but this is 3+ to neutral, in which case it would be no. So we'll have to think about that. That's a tricky one. Okay. And my last one, rank the following from strongest oxidizing agent to weakest oxidizing agent. Here we just need to look up our potentials, and we need to rank them based on the sign and strength. Remember, the larger and more positive the value is, the stronger it will be as an oxidizing agent. The weaker it is, it will be a smaller and more negative number. I'll go ahead and try that out. Okay, I got values of 1.70, negative 1.70, negative 0.44, 0.77, 0.14, negative 0.25, 2.37, and negative 2.37. So those were the voltages. So if I had to rank 1 being the strongest and 8 being the weakest, it would end up in this order: 2, 7, 6, 3, and then here would be 8, 1, 5, 4. This one is the strongest because it's the largest and most positive. This one is the weakest because it is largest and most negative. And then we rank in order from there. All right. If you have any questions, feel free to email me or ask in class. This is the end of Voltaic cells. Thank you.